Yeah, hi, good evening, everyone. Welcome to the revision session. Okay, okay. So this week, actually, we have also conducted a revision session by the TA. So week-wise revision session. So I hope you joined that session. Otherwise, the recording is also available in the calendar. So you can also go through the that calendar event and you can see the recording if you have not joined. Okay, so I think that TA have discussed many practice previous terms questions. So in today revision session also I have some set of questions of the previous terms. So maybe some questions will repeat if those who have joined the TS revision session. So maybe some questions will be repeat. So because I haven't checked the what questions actually TA have discussed. Okay. So other things, if you have any doubt, okay, so you can ask initially if anyone have any query before starting the session.
Yes, sir.
Yeah.
Sir, in the pre and post traversal in the
Hmm.
DHS,
Hmm.
I'm not getting an intuition that if there is a backward edge, then how is leading to a cycle? Like there was a question in previous year
Okay.
where it was like if it is if it is having a forward or backward edge, based on that, if we can say that the graph will have cycle or not.
Okay. So you are saying that how we can conclude that that back edge is represent that graph F cycle, correct?
Yes, sir. Yes, I'm not getting the intuition that how will it contribute in making the cycle or not. Like
Okay.
yes.
Okay. So then we will discuss this because I think I have some questions based on this on in my set.
Oh,
Okay.
So just an idea.
Hmm.
If you want, you can discuss the mock paper also. Just an idea. I mean, we'll
Mhm, yeah,
take
we
it.
can sure we can discuss. Yeah. So we mock questions we have also discussed. Fine. Okay. Any other query? Okay.
I have some mock questions doubt.
Okay. Then
When we can
I
ask
think
at the end or at the we
then
can
we can
discuss
start
it.
with the mock question first. Okay. So I hope many of
Not
you are
mock previous year question. Sorry, previous year.
previous year question. Okay.
Yeah.
Okay. So that I'll take that question. So in
Good evening,
between,
sir.
if so, we will discuss the topic week wise. So at that time, you can ask your query if your question is related to that topic. Yes, Apna.
Nothing. Just I was saying good evening, sir.
Okay. Okay. Then I think we can start with the mock question first. Okay. So
Yes, sir.
I hope my screen is visible.
yes.
Okay.
Yes.
This is the quiz one. Okay.
Yes, sir. It's visible.
Okay. So this is the first question. Which of the following algorithm can be applied to solve all the problems listed below? Finding cycle in a directed graph, scheduling jobs, and where jobs are dependent on the other jobs for resource or result, sentence ordering. Okay, so I hope you have many of you have already solved. So can anyone want to give the answer?
Yes, sir, this is topological sort, I think.
Okay.
Regarding the cycle, yes, we will have since I'm confused in sentence ordering that what is that? First you
Huh,
are clear.
sentence ordering is also based on the dependency problems. Okay, so sentence ordering means you can take like verb and this pronoun things. What order you should take maintain in when you create the sentence.
Okay,
Okay,
ordering.
so actually some dependency is there. You cannot use the any specific type of word before using the another type of word. So some order is specify in the sentence.
Okay.
Okay, so like when we are just facing any problems where the dependencies are given. Okay, so dependency means you cannot complete the current task before completing the previous task, like this.
Okay.
Okay, so this type of dependency are given, then you can think about the DAG. Yeah, that means if you will create the related graph for that problem, so you will get the DAG, directed acyclic graph, and then you can finding out, then you can solve that problem using the topological order, topological sort.
Oh.
Okay, so topological sort, same things. If you apply the topological sort on the cyclic graph, that means you can also detect the cycle, because the topological sort applies on the DAG graph, directed acyclic graph.
Yes. If there will be cycle, then 0 in degree वाले nodes नहीं
यस यस
मिलेंगे।
यस, ये आपको जीरो जीरो वाले वो नहीं मिलेंगे।
हम्म।
ठीक है, सो इस तरीके से वी कैन आइडेंटिफाई द साइकिल इन द डायरेक्टेड ग्राफ, वी कैन शेड्यूल जॉब्स, jobs are dependent to others, and we can also sentence ordering. All these three applications we can use the topological sort. Okay, so now the second question, give code is based on which algorithm. So here code is given, you can identify the algorithm from this. So I think it is easy. Here what we are doing, we are just initializing. Let me just take the pen. Okay, so here you can see that what we are doing first step. So we are initializing min index first at the I. Okay, so and this loop is running from the 0 to length of a minus 1, and we are setting this min index I. After that, we are traversing whole list, and we are finding out the minimum element, final minimum element in the complete list. And after that, we are swapping the current position and the minimum element position. So this concept actually we used in the selection sort.
Yeah.
Okay, so in selection sort, we find out the minimum element, and then we swap the position of the current position and the minimum element position. So we repeat this iteration for the each position. So this concept we use in the selection sort. So this is the correct answer for this. And yes,
And the same idea with taking the maximum element and placing it is that bubble sort, no?
no, bubble
No,
sort.
it is also selection sort.
If you are selecting maximum, then you have to swap with the previous position,
Yeah,
from the
like,
right to left.
okay, with the same idea, like since we are
Same
settling
idea.
down
You
the
can
minimum.
then you can also call it as a selection sort.
Okay, okay,
Okay, but bubble sort concept is totally different.
okay.
So next is this binary search. So here some statements are missing. So you can, if you know the logic of the binary search, then you can figure out that what statement should come at the this missing part 1 and missing part 2 and missing part 3. Total 3 parts are there. Okay, so we have one array here. Okay, we have one array, and k is the searching element, low is the lowest index, and high is the highest index, last index. Okay, so if low is greater than high, that means what we should do, and else what we should do. Okay,
Return
so
false.
yeah, so if low is greater than high, that means we have completed all the comparison, but still we did not find our searching element. So and our, so actually initially what happened, low is set to 0, like, okay, we always start low is set to 0, and high we set to n minus 1. Okay, if our length is n, so n minus 1, this. Okay, so this condition is 0 is less than to n minus 1, and we always select the mid element, and then we change our this low and high index to, according to the mid index. So if this condition is true, okay, if this if our low is less than high, then we will move to this part. Otherwise, if we will move to this condition, so if low become greater than high, so that means our low index is now coming at right side, and high is coming at the this left side. Okay, So that means we have completed the process, but still we could not find out the searching element. So at that time we can return the false. So that means there is no, this element is not exist in the list. Otherwise, what we can do, we can simply find out the mid element, mid equal to low plus high floor division 2, and then first condition we can compare the elements. So we will compare the elements with the mid element. So we are comparing here. If our element is matched, then we will directly return the answer true. Otherwise, what we will do, so we have two recursive call from here. Okay, so we have two recursive call. So we can check from the option now. So what we will do, if our condition is, so this is equal match. Okay, so we can take like the condition if our k is greater than, okay, greater than array equal to mid. So we suppose if we are taking this condition at the second position. So here, okay, so we can also conclude from the else part, because what we are doing here, so we are setting our low as the as similar as input, but we as at the place of high we are setting into the mid -1. So that means for this position, so for this part our k is actually smaller than the mid element. That means what this part is actually representing, this is the left half part, okay, first half part. That means we are ignoring the right half part. So that means this part will be executed when the condition is true if k is less than of our mid element. Okay, so array mid. So else part is executing when this is true. That means so that means this part should be execute if our k is either greater than or equal to, not equal to, okay, equal to is also possible. Yeah, so there is a chance equal to an array mid. So just opposite condition.
For equal, we are handling it separately, na sir? If mid is.
Yes, sir.
Oh, equal, yeah, we have already checked. Correct.
Should be greater than only, sir.
Yes, yes. Okay, so that means this condition should be come at the this missing part 2. K is greater than equal to a array mid. So this is fine. And yeah, so if this condition is true, so what we said here, so this is the k searching part, and what should be the value of low at this time? So this should be mid +1.
+1, yes.
Okay, because mid is not matched, mid is not matched. So that means we will check to the if k is greater than of the searching element, sorry, middle element. That means we will check the right half part and we will ignore the left half part. So we will start from mid +1 to
Mid
high.
+1.
So this should be mid +1. So mid +1. So I think the option first is correct for this. Okay.
Okay.
Yeah.
Okay, sir.
So we will move to the next one. Yeah. This question, a connected undirected graph G has 1081 edge. Okay, so edge is given here. So number of edge is given. So 1081. What can we say about n? Where the n is the number of vertices. So we are asking the number of vertices. What is the number of vertices possible? So for the graph, this is the undirected graph, okay, connected graph. So that means what are the minimum number of vertex possible and what are the maximum number of vertex possible. So you know, if you know the formula of the maximum number of edge in the connected complete graph, okay, suppose if our n equal to 5, so what are the maximum number of edge possible and what are the minimum number of edge possible for this? So minimum number of edge possible, if you have 5 vertices, so that means at least 4 edges required to connect all 5 vertices. Correct? So this is minimum number of edges 5 minus 1. Okay, so that means we can say that n minus 1, and maximum is n into
n minus 1 upon 2.
n minus 1 upon 2. So that means 5 into 4 divided by 2. So total 10.
So this formula is for n into
Max
n minus.
maximum number of edge in the if our graph is complete graph means our each vertex is directly connected to the all other remaining vertex. Okay, so this represents the
Okay.
maximum number of edge possible for given number of vertex. So you can use directly this formula. So the question is now reversed here. Okay, so that means here edge is given, so what are the maximum number of vertex possible? So if our graph is not completed, not complete graph, okay, and so like our graph is connected in serial manner like this, all vertex are connected like this, okay, and now you have total 1081 edge. If you count this edge,
So
so
how
that means
1081? It should be 1080, no?
no. If you have suppose three edge in the graph, I'm taking example 3 edge in the graph. So if you connect 3 edge, so that means you need at least
4
4
vertices.
vertex. So
4
one vertex should be
vertices.
greater. So 1081 plus 1.
Oh, yeah. Sorry.
Okay. So that means maximum number of vertices are possible 1081 plus 1, 1082. Okay. So that means answer should be come from these two options. So this is you can remove equal sign. Okay. Now you can identify the this you can apply this complete formula.
47.
Okay, so simply apply this formula like 47 into 46 divided by 2 and check what value you are getting, and same for the 46 what value you are getting. So if you are getting more than this, so you cannot take that number. Okay, if you are getting less than, so that you can consider the answer.
One quick question: the edges are 1081, so the nodes are our tests are 1082.
Yes, one more than number of edges. So this will represent the maximum number possible. Okay. And for the other part, for the minimum part, you can simply check this formula for each this number. If n is equal to 47, you can check what value you are getting by this formula.
Excuse me, sir.
Sorry, what do you mean by that? Can you just elaborate a little?
So we have already checked now if if number of vertices are given, so what are the maximum number of edge possible? So we can calculate by this formula.
Correct, but that is for the maximum. For the minimum?
So here question is reverse, but here a number of edge are given. Okay, we are looking for the vertices. So that means this should be the maximum for this number of vertices. So here we can say that this should be the minimum number of vertex required for this number of edge.
I mean, how are you computing that? Can you just? I mean, 1082 is
no, sorry,
clear.
1081. Yeah, this is the number of edge. This okay, this part is clear. This is the
that is the number of
vertices. Yes,
okay.
This is the maximum possible.
Yeah.
Okay, so if you take
Excuse
47.
Me, sir?
Yes.
If we connect the nodes in triangular shape, then 3 edges, 3 vertices will come.
No, but that is not the maximum or that is not the minimum. So in this case, so this is the maximum case.
Okay.
Okay, but this the same graph you can connect by the 2 edges. So this is the minimum case. So here for 3 vertices, if n equal to 3, number of vertices are 3. So minimum number of edges will be 2. Okay, but maximum you can find out by n into n minus 1 divided by 2. So 3 into 2 by 2. So you will get 3. So this is the case.
Okay, here connected graph means
not connected, complete graph. So this is a complete graph. Here each vertex are connected to the remaining other vertex directly.
Okay.
Okay, connected means all nodes should be connected. Some path should be there from each node to each other node.
Okay, means
we have to take in the sequence order. Connected graph means.
So connected means, let me just explain. So connected means
Define graphs and connected graph.
so if you can traverse each node, so suppose this is a graph, okay, this is the graph. So if you can traverse the first node, so this is 1 2 3 4, so you can traverse from 1 to 4, okay, because you have one path. Okay, you can traverse 1 to 3, you can traverse 4 to 2, you can traverse between any pair of path in this graph. So this is called as a connected graph. Suppose in the same graph we have added one new node like this, but there is no edge is there which is connected to this first part. Now this is called as a disconnected graph, because here there is no path from 1 to 5 or 2 to 5 or 4 to 5 or 3 to 5. Okay, so this is called as a disconnected graph. So here it is given that connected undirected graph. So graph is connected. Now we are looking the answer for in the connected case. Now complete graph is the different terms. Complete graph means if you have 4 nodes, suppose, so that means 1 2 3 and 4. Okay, so how you will make a complete graph? So complete graph means this one should be complete connected to all 3 nodes. So 3 2 4 directly. Okay, now same for 2 should be complete to 1 3 and 4 directly. So we will directly connected this. 3 should also be connected to the all other remaining vertex. So 1 and 2 is already connected, and now 4. Now same things, now 4 is also connected directly. So you can see that this is complete graph. Okay, where the direct edges for each pair in the graph you have direct edge.
Okay. In this case, maximum edges is equal to n into n minus 1 by 2.
Yeah, in this case, maximum edge are n. If number of vertices are n, so n into n minus 1 divided by 2. You can directly calculate this number of vertices. So 4 into 3 divided by 2, so this is 6. Total 6 edges.
Can we say that if a graph has the maximum number of edges, then it is a complete graph? Okay.
Okay, so maximum number of edges are possible in only complete graph. Okay, so this part is clear. Then you can simply calculate. So we have already checked this 1082 part. Now for this part, you can simply calculate. You use calculator like this. So 47 into 46 divided by 2. So this is 23. Now you can check 470 and so how much value you are getting? So 1 second, 420 and 141. Okay, so 17748 and 9 and 108. So you can see we are getting, if we are selecting this 47, we are getting the same number 1081. Okay,
but 1081 in this case will be the edges, isn't it?
Edge. So this is the number of nodes, and if we have this 47 number of nodes, so in the case of maximum number of edge, you will get this 1081. So this is the same things now. So here we are asking what are the condition is possible. Our n may be equal to this 47 or equal to this. In between our n may be come. Okay. So this is the minimum case. This is the minimum number of vertex possible. This is the maximum number of vertex possible for this number of edge.
One second, please. 47 n into n minus 1 by 2 is what you're saying. So number of vertices is 47.
Yes.
So
if we have only 47 vertex in the graph, so you can achieve this number of edge by creating the complete graph 1081. Okay, so this is the minimum number of vertex possible for this 1081 edge, and this is the maximum number of vertex possible for the same number of edge.
Okay,
so this third option is satisfying our criteria. Okay, so next is what are the appropriate data structure for the BFS and DFS. So if you have already implemented or you have seen this algorithm BFS and DFS, so I think you can remember in BFS we used queue and DFS we used stack. Okay, so this is direct. You can mark the answer if you know the implementation. Yeah, for this question number 6 and 7. So in this question, the some scenario is given. So here you have 100 box, one box is open, and you have one key in that open box, and you don't know that is related to which other closed box. So what are the so in this question we are asking that what are the worst case time complexity of this algorithms? Okay, and seventh question we are asking that if we try to open one box by the key and it takes 10 seconds, so what is the total time required to collect the all gift collect the gift? Okay, so this is also a worst case situation, maximum time we are asking here. So this question is very related to the your worst case situation for the selection sort or insertion sort, like this these algorithms. So if you just relate the total number of compare steps in the selection sort and insertion sort in the worst case, so that is very similar here. So here one box is open. So here 100 boxes are there. So suppose this is the box, like, okay, and you have total 100 box. So this first box is open and you have one key. Now in worst situation you have to try this key with the all remaining 99 box. Okay, and you are trying this 99 box, and suppose you get the by this key the last box is open. Okay, so when you try all 98, so all these 98 box are not open because the key is not matched, but when you try the 99th box, that box is open. So that means in worst case you have to try with the 99 box by the first key. Okay, then you will get the another key. So now two boxes are open, the closed box number are 98. So same things in the worst case, you have to try with 98. Then you will get one more key. Then you have to try with the remaining closed box, so that is 97. So in this manner you will try with the each box, so till 1. So this is the total number of steps we are getting. So if you add this series, so 99 plus 98 plus 97, so that means if you are taking n equal to 99, so you can directly apply this formula. So 99 into 99 plus 1 and divided by 2. If you are taking n equal to 99, okay. If you are taking n equal to 100, so you can apply the n into n minus 1 divided by 2. So 100 into 99 by 2. So you will get the same 4950 value. Okay, and each box is taking 10 seconds, so you can add one more second here. So in this case, so this answer you will get. So for 7th, our answer is this 49500. But for the complexity thing, so this is very similar to. So that means in the first step, our algorithm is taking n minus 1 steps. Okay, in next step n minus 2 steps, then n minus 3 step dot 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 1. So that means we are concluding this n into n minus 1 divided by 2. Okay, and when you just conclude this equation, so you will get n square by 2 minus n by 2. Okay, so this is the highest order of terms. So this will become the complexity of this algorithm. So this option is the correct answer for this. Okay, and for next question, you can see we are getting so this 49500. This is the answer, maximum number of second required. Yeah.
Nothing. It's okay.
Okay.
Sir, here you have not added the 10 second.
Yeah, I've added no. So when you calculate this for series, you will get this 4950 only.
Okay.
Okay, you will get 4950. When you are adding 99 plus 98 to 1, you will get this. But when we multiply by 10, so you will get one more zero. So this is the answer. Okay. So this is the next. So here this is also a type of searching. So but in this question you can just check some base conditions are given. You have to check the code for each question here. Okay. Okay. Suppose first question what is given. So suppose we are giving this input to our code. So here select the option which demonstrate the worst case behavior for above search function where L list size is 10 to the power 6. Okay, so this size is given and we are passing these options to this code. So which function will take the maximum worst case time? Okay, so you can see what value we are passing this L and -1 and 1. So let me just reduce the size. Okay. Okay. So in this code, you can simply pass the code, pass the parameters to the function and check what value you are getting. So here, so this is X value. Okay, first value is the X and second value is the B here. So in general, what we are doing in this code, we are trying to search element. Okay, and based on the input, so this is just defining the criteria, how we are dividing the list. So in binary search you have already seen. So in binary search we always divide the list into two parts. Okay, we check the middle element, then we check the left first half and second half. Same things in the ternary search, we can just divide the list into three parts every time. Okay, so if our element is not matched, so we will check like 1/3 position first. So we have like this list and we will check 1/3 position and 2/3 position, and then we will check in which part our element is coming. Okay, by looking the condition. So this is called as a ternary search.
Yeah, sir. How you from the code find this is a tertiary search is happening? Suppose I don't know the tertiary.
This is not a ternary search.
Mm-hmm.
This is n search. Actually, we are passing the value B, and this B will decide what type of searching we are doing. If you are passing B equal to 2, so it will become a binary search.
Mm-hmm.
Okay, so that means this B is deciding how much time we will divide the list. Okay, so you can see in this loop, so this for loop it is running, so 0 to B -1. If suppose this B equal to 2, so that means 0 to 0 and 1, we have two value, and we will divide our list by 2, so n by 2, so our list will become half. Okay, so in this manner we will just check for the two halves in our list. If we pass this B equal to 3, so because of that this number is given, n is here, n search. So if we are passing n equal to this 2, so this become bi. Okay, binary search. And if we pass as a 3, then it become a ternary search. So here we are passing the value, so that actually we will pass in the code and our algorithm will work based on that. So this is the idea of this code. Now we can pass the parameters. Okay, and we can look which algorithm will take the worst case time. So what is the maximum time required? So here first value, just remember that this is the X value and this is the B value. So we are passing -1. Okay, and each function we are passing -1. Okay, so this is okay, and in B value we are passing 1 in the first option. So suppose if we passing B equal to 1, so how many steps our algorithm will run? Okay, so this is the constant operation. You can see if n equal to 0, so n is our length, So this is constant operation. Yeah, this is a loop. So we have to check how much time this loop will run. So if you are passing b equal to 1, so that means range is only 0. Okay, and this range is now 0. So here you are passing 1. Okay, and I will become 0. So here 0 into n. So 0 into n, n is our length. So this part will become L0. Okay, L0, and we have only one step here. So you can see we have only one step. So this is also a constant operation. So we are simply comparing the first element by the x. So this x is a searching element. So this is also become constant operation because one step is running here. Same things, this is also a constant operation. So till now we are running all constant operation. Okay, and in the next part here also you can see for I in range, same things. Okay, so 0 and 0. This is also a single loop, only one iteration, and but this contains this recursive call. So we have to check this recursive part here. So if this condition is true or not. Okay, so I into n divided by 0. So this will become, so first statement will become L0. Okay,
Sir,
because
for the b is equal to 1, this will not occur. I mean, this loop will not done because of the range is not valid range 0 to
okay,
0.
so this
All
is
this.
b minus 1 now. Oh yeah, correct.
Yes.
In above case we are taking 1, so this will run one time. Okay, fine. Yeah, so here we are taking this b minus 1, so 1 minus 1 becomes 0, and our range should become less than 0. So that means this is not valid loop, so this will not run. And here this is only single statement condition. So this condition is true, then we are calling recursively. Okay, then we have to check this condition. So what condition we're getting here? So b minus 2, so that means 1 minus 2. Okay, this is L. Okay, into n. Okay, so n is our 10 to the power 6, and floor division, this p equal to 1. Okay, so what overall value we will get here? So this is minus 1 into 10 to the power 6. Okay, so this is actually last element. Okay, let me check. So this is about.
No, sir, it will not be last element. My L minus 5000.
Oh, okay.
It
Yeah,
will
this
be
is
first element.
Yeah, first element. So minus 10 to the power 6. Okay, so this will become first element. And then we are checking our x value is greater than L first element. We can write this L first element and less than equal to L minus 1. Okay, so this is now range, and this x value is actually minus 1. But our element is actually list is sorted from 0 to 10 to the power 6. Okay, so because we are creating this list that will start from 0 to 10 to the power 6 minus 1. So this first element should be this. So you can see this condition is not true because minus 1 is not greater than 0. Okay,
Sir,
so
how
this
is L of 0, the L of minus 10 to the power 6?
So this actually, if you know that, we can also start indexing from the last element. So suppose if we have 5 element in the list, so like 1, 2, 3, 4, and 5. So this is the positive indexing 0, 1, 2, 3, 4, 5, and this at the minus 1, minus 2, minus 3, minus 4, minus 5, like this. Okay. So if we are writing minus 10 to the power 6, so that should be the first element. Okay, so we are just writing first element as a L0. So here L0 is the 0, and this value is the 10 to the power 6 minus 1. So this minus 1 cannot be come in between. Okay, because minus 1 is less than 0. So this condition is also false. So this will also become a constant operation. So when we are Yes.
But sir, here we are comparing the values that we'll get at the index of -1, not the -1 itself. So it should work, right?
No, we are comparing x value. No, so x is in this value is
Yes, we are
-1.
comparing x with L of -1. So we will compare whatever element is at -1 index.
So I'm also comparing with the value. So this -1 is the last element. So this is 10 to the power 6 minus 1. Okay. And first element is the 0.
So it's in the sequence 0, 1, 2, 3, 4, 5.
This
The
is
list
sorted
is like
list.
this, right?
This is sorted list.
Okay.
It is given in the question.
Okay, sir,
So
got it.
you can see where L equal to list range
Okay,
of
sir,
this.
got it.
So all are the constant operation performing. That means it will take constant time. Okay. So this is taking constant time. Now same things we can check the next. So here we are passing 2 now. So in 2 case, once again,
Login.
b equal to 2. No, we have to check this. It is taking login or not, because we are
No,
set to -1.
Yes, we have to check because few loops will occur.
Yes. So let me delete this. Okay, I copy this. So in second option, we are passing -1 and 2. So -1 and 2. Okay. Now the searching element is the same and b become 2. So this is the constant part. This will run 2 times. Okay. So 0, 1. This 2 times. Okay. And the first value will become. So this first value will become L 0. So 0 into this L0. Okay. Is equal to x or not. And second value will become, when we are passing 1, so it becomes 1 into 10 to the power 6 divided by 2. Okay, so 2, this will become 10 to the power 3. So that means middle elements. So this is also a constant operation, because we are finding out the 2 value here, and this we are comparing with the last element. So what happening in this list? We have a list. We are comparing with the first element. Okay, suppose we have one list. We are comparing with the first element in first iteration. In second iteration, we are comparing with the middle element. Okay, and in this next condition, you can see we are comparing with the last element. Our what we are comparing? X. Okay, so we are comparing with the first, middle, and last by these 2 conditions. So this is constant operation, and now next things, this loop. So this will run now 1 time here. Okay, so 0 only. So b -1, 2 -1, and 1, and 0 for I equal to 0. So now this condition is true or not? So we are searching -1. Same things. So 0, the first condition will become 0, and is greater than -1 is greater than. This is I plus 1. So I plus 1 will become 1, and this is okay. So this is 10 to the last element. L 10 to the power.
Not last, is the middle element.
Oh, okay, b equal to 2. Yeah, middle element 10 to the power 3, we can say. So still this condition is not true, because -1 is not coming in this range. So this recursive call will not run, and this is become a constant operation. Now next, this condition. Okay, b -2. So b we are taking 2. So 2 - 2, 0.
It will also not work.
This first condition will become L0, and second L -1. So this is also not work. So this is also a constant operation. And what we are looking the worst case behavior. So this is also constant.
In the first side, it seems like it will be log n, but it's constant.
So I think this 1, 2, 3 it taking time. Suppose if we take len of L, so I think this will take the maximum time. So because
we have to check only how many times running in the loop, not the steps, because x is already -1, which is never in list.
But still we have to check how much our algorithm will run for the any particular input.
This function called recursively, so we have to check.
Yeah. So if we pass -1 and len, okay, so -1
Sir,
and
can
10 to
it
the
be,
power.
sir, is the answer can be in the form of log n with different bases, like log n with base 1, base 2, base
No,
3?
actually not in that way.
Because in the
Because
last procedure, we have already seen that 2 is not log 2, it's constant time.
constant time, yeah. But it is depends on the searching element also, because what happened we are directly comparing the first element and last element also in this algorithm.
Oh,
So
yes.
if our elements is coming in between, then it will take log n time. Okay, but for this input, this is not taking log n time, and it is directly returning the answer based on the first and last comparison and middle element. For this case, when we are taking b equal to 10 to the power 6, so this loop, first loop, you can see this will run overall 10 to the power 6 time. Correct? So 0 to 10 to the power 6 minus 1. So here it become order of n. Okay. So you can see, I think this is the worst case then. If it is running order of n times, first loop, and here also it will run same. So 0 to b minus 1. So this is become 10 to the power 6 minus 1, 2, like this. Okay, 0 to 10 to the power 6 minus 2. This will also run the same in manner. So in this manner, you can figure out that, so for last input, when our b value is increasing, so our algorithm is running the maximum number of times in this. Okay, for constant value 1, 2, 3, our code will remain as a constant. So worst case behavior we are getting for the last option.
That is length of L, right? Okay,
Yes.
length of L is given there. Okay.
Yes.
But for example, in case of 1 and 2, we know that the binary search takes lesser time than searching each and every element. So shouldn't the 2 like take lesser time than 1?
Yeah, but here input is -1. So -1, actually we are also we are directly returning the answer based on our comparison. So we are checking -1 is coming in this range or not. If not, then we are returning the answer. So okay, based on the input. But if we pass any input which is coming in the range, then yeah. So if we are passing 1, then it will take I think okay, so if we pass any, so we have to check the code once again for this. So if our element, yeah, so in that case we will pass recursive call. Okay, so if our element is coming in between range, so our recursive call will perform. But what happened, we will just so what b value we are giving 1. Okay, so it will take approximately linear times if we are giving the 1 time. Okay, because we are dividing the element by the 1 element only, first index. So that means in first iteration, our one element will be removed, and we will check the n-1 element. And the next recursive call, we will remove one more element from the corner, then we will check n-2 elements. So in this way, if our b is equal to 1, then it will take linear time. But if we will pass b equal to 2, then it become a log n.
Like if the element is present in the list.
Yes, correct. Okay.
So
if our element is present in the list and coming in the range of 0 to 10 to the power 6 minus 1, in between. Here what happening, actually this -1 is just coming from the before the first element. Because of that, it is taking constant time. Okay. So yeah, if you pass b equal to 2, it become binary search. It will take log n time. If you pass b equal to 3, it become same turn log base 3 n time, like this. But suppose if we make this b equal to n, then again it will become order of log linear search, like this.
Right. Okay.
Okay. So that means there's no benefits if we increase the dividation part. So we can conclude this. So if suppose if we think about this, so if we increase the dividation part of our list, so it will not will give the help for the efficiency. Okay. So if you are taking
ternary is not better than binary.
Yes, not better than binary, because in ternary search, your comparison will increase actually. So in every steps you have to compare.
We will be able to go to the
1/3 part.
1/3 part, right? Instead
Yes.
of half.
Yes. But in worst case, I think again.
No, leave the worst case. Considering the element is available. Okay, in this case we don't have the element. Leave this case. Otherwise, if the element is available in the list,
yes,
then which is better? Binary is better, or dividing the list more than 2 or more than 3, or say for example n. Is it n better or binary better?
No, n is what is n length of the list?
Yeah.
So
it is, sir, also depend on the input, because if you find for the middle element, then binary is the direct.
Because of that, we always discuss about the worst case. Okay, so best case we are not discussing. In each algorithm, we generally discuss the best case worst case complexity.
But in this problem, we have already given the what we are searching.
So for if you are taking b equal to 2, for example, binary search, so what you do in the each steps, actually you compare the element by the middle element, one element only. Okay, after that you have only half part, either or left or right. Okay, if you're taking b equal to 3, then some number of comparison will increase at the each steps. Okay, so in that case you have to compare
the first loop. You mean to say because of the first loop itself, the first
yes.
already doing, so there we will already seeing if we make n, already it will become a naive search, as it is going to divide it by n times the loop runs, it will find the element.
Yeah, correct. So in b equal to 3 case, you are first checking 1/3 position. Okay, if either it is smaller than or greater than this side. Okay, then if it is not satisfying this, then you have to compare by the 2/3 position, like this. Okay, so if our element is smaller than or greater than, so then you after comparison both element you can conclude. So like where our element is
if
coming.
it is 4, it will compare 3. It will see 3 elements in the first loop itself. 5 means 4 elements, and then n means n minus 1 element. In that first loop itself it will do. So that's what you are trying to say. It's more comparison.
Yes, correct.
Okay,
so our comparison is increasing at each step. So if our b equal to n, then it will become linear.
I have a question. In the scenario where b is the length of the list, that means I'm taking only the first element, correct?
Same manner. So that means you are dividing the list at the each. You are comparing the element between each element. So what you are doing, you have total like 5 element, and you have taken b equal to 5. So first you will compare with this element, our x element, x is greater than this or less than this. Then you will compare with this, x is greater than this or this, like this. If you are directly matching, then you can directly match this.
So basically, it is big O n, is it?
It become linear search now. You are comparing the element by the each element.
Okay. Thank you.
Yeah. So in this manner, you can just. I think the second question is also related to this. Open. Okay. So here, select the optimum parameter for the above and such function with respect to the least number of operation. We are the same. Okay. Here we are asking the least number of operation. So I hope we have already checked.
Second, third option.
This one, now we have already checked here. This where our no loop is actually running. So this second, this is also exit. This is also exit. So here you can just look, and so this one value actually this is the correct one, least number of operation. Okay. Yeah, next is this one. This is also related to complexity. So in actually mock, we have given this type of lengthy questions. So because you have enough time to do this, but in OPP question generally we will not give that much of lengthy. Okay. So
you
because it will take.
You mean Quiz-1 or OPP?
Yeah, Quiz-1.
Quiz-1.
Okay, so actually for mock we have collected the questions which are actually tricky questions.
So it's the same level of complexity in the exam or higher?
Lower.
Lower, okay.
Okay. So here same things, some input is given, the list is given of n integer, many duplicates are there, such that the number of distinct integer is so this log n value is given. So you can just write the each things according to the question, and you can check what value you will get finally. Okay, so total n elements are there. Okay, and but you have duplicate numbers, so the distinct number are log n. Okay, this is the distinct number. We use the below algorithm to sort this list. What will be the worst case complexity for this algorithm? So this algorithm we are following to complete this. So in first steps, what we are doing, iterate over all elements of L and create an array A1 of all distinct elements. So here we are iterating all elements. So this means this will loop, this will run overall n time, correct? So this loop will run overall n time because we are iterating each element, and we are creating a list A1 that actually contains the distinct elements. So this list contains the distinct element. That means length of this list is log n. Okay, because we have log n distinct elements. So A1 length, just remember that this is the log n length list. Now sort the array A1 created in step 1. If the size of A1 is S, then the step takes is S log S. Okay, so here example is given. If our size of this list is S, then it will become S log S. So maybe using the merge sort or quick sort algorithm. So it will take n log n time. So the same behavior, now input is log n. Okay, so just write in the same manner. So log n is the size of A1, log n into, so this is similar to S, and log n log n. Okay, so this becomes the complexity of sorting this A1, log n log n.
Would you mind explaining this once again, please?
Because if our list size is n, so we are taking n log n time to sort. Okay.
Yeah.
So here example is given. If size is S, then we are taking S log S. But here size is of this A1 is log n. Okay, so we are putting log n at the place of S in the each here.
Okay.
Okay, so we are getting log n log n.
So n itself is S log S is what you're saying, or?
Yeah, so here this is given as an example. If the size of A1 is S, but actually we want to represent the complexity in the terms of n. Okay, this terms. So we know that our distinct elements are log n. So we can represent the complexity in this terms. Log n log n. Okay.
So distinct log n is coming from?
This is given in the question.
Okay.
So such that the number of distinct integer are log n.
Log n. Okay.
Okay. So this step is taking log n log n. Okay. Now next, move to the next one. Create another array A2 containing all 0 equal to the size of A1. Okay. So A2 is a new list, and all it is containing 0, and size is the same log n. Okay. A1. So this will also take log n steps for each element E in L. Okay, so here this is the list L. That means it contains the actual n elements. We are traversing each element from the L using binary search. Find position P. Okay, find position P of E in A1. Okay, that means we are traversing the our actual main list L, and we are applying the binary search on the A1 list, okay, which contains the log n element. So for each element, how much time it will take?
Log n.
Log n, correct. So because here size of the A1 is log n, okay, and binary search takes log n, okay. So we will replace n by log n. So it will take log n, okay. So this is the size of A1 actually. Because of that we are writing this one. So for each element it is taking log n steps, and we are incrementing the value at position P in A2. So we are simply incrementing the position. So suppose we are looking for the 2 element, then we are incrementing the one count. This is basically a count list, so it will take constant time. So how much time this loop will complete take? So here total elements are n in this list. We are looking each element in our A1 list using the binary search. So one element is taking log n time. So how much n element will take?
Yes.
Total
N log n.
So n into log n. Okay. So this is the overall complexity for this 4th steps. Okay. Now initialize a new list.
Sorry, once again. But our distinct integers is log n. Okay.
Yes. Okay, and these are sorted list actually. So we are
that fourth B is saying, I'm not very clear. Increment the value at
increment the value at position P in A2. So corresponding value. So here actually this is A2. Okay, and A1 we have the actual element. So what element we have? So suppose if we are if our E is matched with this P index like 3, so we will increment the counter of 3 by 1. So this is A2 is basically maintaining the frequency of each distinct element.
So basically we'll go through the entire entire n that is part of the list.
Here for increment there is no need to traverse the entire list, because you can directly increment by this like A2 and P index equal to plus equal to 1, like this directly.
Yeah, so that also takes n order, right?
But okay, yeah, that you're talking this n. But overall complexity I'm asking. So overall complexity, this is n, and this is n into log n. So if this is higher, so we will consider this complexity for the overall.
Why n? That's what I'm saying. See, A2, the length is log n, right? A2's length is log n,
but
right? So,
we are doing this operation n times, no? And this is constant operation. So this B is a constant operation. We are simply
okay, so
incrementing
you
the
mean,
value.
so will it be like log n plus n times log n? Maybe in complexity we will ignore that log n, which is adding up, but
No, this A2 is a list. You know the P index. You are simply incrementing the value y1.
right. So there's increment. We are doing it for log n times, right? Because the
No,
length of
n
A2
time,
is log
n time. This loop is running under this for each element E in L. So
but
L is the actual list which contains the n integer, duplicate integer. Okay.
Right.
Okay. So this B step will run n time, but we are applying the binary search on the A1 for each element of the L. So it will become n into log n.
So here A1 is the distinct set of elements, or A2 is the distinct set of elements.
A1 is the distinct set of element. A2 is the counter that frequency list for the each
frequency
element.
list. Okay.
That initially contains the 0. We have initialized here in the third step.
Right.
Okay. So the overall complexity will become for this 4-step maximum n into log n. This okay. And in the 5th step, initialize a new list with ls. Okay. So this is ls.
ls, I think blank list, just blank.
Okay, yeah, this is ls list. Okay, fine. Yeah, this ls list is the blank list. Yeah. After that, what we are doing, we are simply appending the element. So each element, create a sorted list using A1 and A2. For each index I of array A1, append A2. Okay, fine. So this, I think if you remember that, this problem we have already solved in the one programming question in the week 2. If you know that. First, what we are doing, we are simply counting the frequency for each distinct element in A2. And after that, in last final list L, for each distinct element, suppose that this is the first element 0, and this is the frequency of this like 5. Okay. So what we will do, we will append this 0 5 times in this list. Okay, so 0, then 0, then 0, then 0, and then 0, like this. Okay, and second distinct element is 1 and frequency is 2. Okay, frequency is 2 in this list. So we will append this one element 2 times. So 1 and 1. In this manner we will create this list, and our list will become sorted. So it will take or total n steps, because we have total n elements in our main list. So we will perform total n append operation, so it will take n time. So this last step will take order of n.
Sir, how will it take n? Because for let's say for 5, we are appending it 5 times, then 2 times. So it's not just 1 plus 1 plus like till n. So it's not.
But what happened actually? This A1 contains the distinct element of the same list. Oh, let me take example for this. Okay. So suppose if your list is like this 1, 1, 1, 2, 2, 3, 3, 3, like this, okay, and 4. Okay, so this is actual L list. Okay, it contains 1, 2, 3, 4, 5, 6, 7, 8, 9 element. Correct?
Yes, sir.
Okay, now we have created one A1 list. So A1 list will only contain the distinct element. Distinct element are 1, 2, 3, and 4. Correct?
Yes, sir.
And A2 list is maintaining the frequency of each element. So 1 is repeated 3 times, 2 is repeated 2 times, 3 is repeated 3 times, and 4 is repeated 1 time. If you will add this frequency, you will get the same number, 9.
Yes, sir.
Okay.
Okay. Yes, sir.
So because of that, this.
So instead of doing a loop, we can just multiply, right? A1 1 into 3.
We are doing the same things, but we are actually maintaining one final list, LS. So we are performing append operation. So we are reading the distinct value, and we are appending 3 times in the same list.
Okay. When we take a list, okay, suppose we are.
I think you are saying this operation like L.
The same value 10 times.
So like into 5 times.
Yeah, is that a constant operation or is that 5?
This is a 5 operation. It will take 5 steps. Okay, so Python actually gives some short tricks, but internally it takes the same number of steps. Okay, so in this manner, now final steps will take order of n steps. Okay, now you can see which steps is taking the maximum number of times now. So we have all sequential steps: first 2, 3, then 4, and then 5, and then 6.
Okay, so, this n log n.
So you can see this n into log n part is the maximum part. Okay, it will become a complexity of overall algorithms. Other remaining part is actually taking the less than this. So that part will be neglected. So that means this is the final D is the answer for this.
Sir, I have one request. Can you write a small code for ON plus login? Simplest code for ON plus login. What should give me such?
You are talking about this?
Yes, this option. Yes.
So any code for this?
Any code for this.
Okay. So we have to think about the problem for this. Okay. So I think what you can do? 9 steps. Okay. Login.
See, we can do a binary search for binary search and print n elements. So,
but no. Actually, if you are performing binary search for n element, then it becomes a n log n.
No. What I'm saying is, right, let us see, he just wanted a sample algorithm, right? So for sample algorithm, we can run a for loop, which will run n times. Okay. Print I or something like that. Okay. And then we'll have another thing. The entire program, right, which is print and which will do a binary search, will run n plus log n times.
So suppose if your code, first part of the code is performing simple one loop. Okay. Okay. So let me just write this. Okay, you are saying that we are writing n plus log n
code.
So we can also write this for this as a big O n, because n is the highest term.
No.
One use case of we can demonstrate an example for this. You can just compare two kind of searching, linear search and binary search in a single example. This will take this n plus log n time.
No, it will get n square log n time.
No,
n
it
plus
won't, right?
log n.
Searching.
You are searching linear search and then count how many times this linear search do, and then
So
binary search.
so can you write the code such a way that it will do n plus log n will come?
1 second. Delete this. So simply what others are saying, actually you can simply write one code where in one part of the code you are traversing the complete list, okay, and another part of the list you are simply applying the binary search on one element.
Okay, just write it, sir. I'm not able to visualize it.
Just write a for loop, sir, first.
Okay. So suppose if you're writing some function, so like the f1, and you have list, okay, and so in this code, like you can run a loop, so like for I in range like len of L, okay, and in this element you are performing some operation, so
print
maybe
print I. You just wanted a sample,
print
right?
I. Print I.
So,
okay. And in the another part you are suppose you have another function like that is binary search, okay, so def binary search, okay, and lx like this, and because you know that binary search operation takes log n time, and we are calling this function from inside this function, okay, and like the binary that binary search, and we are passing some list and there's some element like 5 or things, okay, and we are like printing here.
So that means you are introducing recursive function.
This is not a recursive function, no, this is actually a separate function, but we are calling this function from this another function, okay.
Correct.
And on the one element.
Then the complexity will be on, na? Why I will call it on n plus log n.
So you can write O of n. Yeah, correct. This is just a representation. If you are writing n plus log n, okay, we can also write like big O of n. This is because we can remove this part. So why you are confusing if you have written one step here in the log same n terms? You can ignore this also. Okay, what happens sometimes if suppose this n is not this is another parameter, okay, this is like m, then you have to write that totally separate, but we can if you are writing in this manner, so there is no problem in this, but generally we takes the highest order of term, so that you can also ignore this. Okay, this is not we cannot say that this is incorrect.
Okay, sir, no problem.
Okay.
And sir, one more thing, log of log n will be less than log n, right?
Yes, correct.
Okay.
Yes.
Okay, so yeah, this is next is consider the following variation of the merge function where the input list L1 and L2 are sorted with unique elements. So this another code is given for the merging operation. So then what is asking, what does L3 contains after string merge L1 and L2? Okay. What are the options? L3 contains the intersection of A and B. L3 contains the union of A and B. All values. Okay. Yeah. So then you have to once again you have to go through this algorithm, and you have to check what actually algorithm is doing, what code is doing.
Sir, just 1 minute, sir. Sir, the answer of question number 10 will be n log n or n log n. Because n log n.
Last one, D.
But sir, D more than D, n log n will be a higher figure than D, na, sir?
But where you are getting L log n?
First option.
No. Which step you are getting L log n steps?
First, second step, sir.
Second is log n, log n, not n log n. Okay, we are not getting this n log n at any step. Okay, because when we are sorting this A1, the size of A1 is log n. Okay, so total become log n, log n. Now just check the implementation of this strange merge, how this code is working actually. So we are setting I equal to 0. Okay. So both value are set to 0 initially, then length, then L3 equal to empty list. Now we will check this I plus j is less than equal to m plus n. Okay, this is one while loop, and we are looking this if I equal to m. Okay, then we are appending all the remaining elements of L3. Okay, so this is simple. We have two lists. Okay, so L1 and L2. Okay, this is L1, L2, and we have like some index 1, 2, 3, 4, and like here 1, 2, 3, 4, 5, 6, 7. So size may be different. Because of that, we are working this. So and we are creating L3 list. Okay, and in each step, what we are doing, if our I will become equal to m, suppose we are taking m for L1 or n for L2. So at any step, if our I, so we are starting from I equal to 0 and j equal to 0. Okay, and if our I become m, that means our I list is completed. Now we will shift our all element in of L2 into our final list L3. Okay, so this is the one case, and each time we will increment our j one time. So this is the one condition for if. Else if our j
Sir, one thing you can do. This is a exit convertible. If I come to these first two condition, if I equal to m and j equal to n, then actually one of the sorting is completed. Now I am just appending the list. So the
Yes.
interesting thing happening after that actually, I believe. You can go ahead, sir.
So what I'm doing, when I become equal to m, that means our I list, this L1 list is completed. Okay, and what are the remaining element we have in the L2? We will shift all element one by one into our final list.
Correct.
Okay, so this first condition is doing this. If we are, and every time you can see we are incrementing j by 1. Okay, thus just reverse condition, if our j become equal to n, that means our L2 part is completed. In that case, we are shifting all first list. If any element are remaining in the L1, then we are shifting all element one by one into final list L3. So this is two step. Else, so if, elif, and okay, so this part is completed. Okay, now next iteration is started. If I is less than m and j is less than n, that means both our pointers. So initially we are starting from I equal to 0 and j equal to 0 like this. Okay, so this is from 0. So at that time, if our I is not equal to m and j is also not equal to m, that means we have a remaining element in the both list. So then we are comparing the element. So if L1 I is less than L2 I, then we are shifting L1 I to L3. Okay, then we are incrementing I. So this is, I think, simple merge sort. I think what is strange in this?
No, sir.
No, this is
When
not.
it is equals, it's not happening.
Yeah. Okay. So I think this is some changes there. Okay. So what we are doing? So yeah, if our L1 element is smaller, okay, then we are moving our L1 element into a final list. But if our both elements are same, L1 I and Lj both elements are same, we are not doing anything. We are simply increment our both counter. Okay, if our suppose here is also 2, here is also 2, so if our both elements are same, then we are increment our counter, we are not doing anything. But
Okay, so we are excluding common elements.
Common elements, yeah. So we are excluding all common elements in the final list. and those are not common, we are including in the final list. Okay, and this elif part is the just reverse of the first part. So if L of I is greater than L to J, then we are shifting this element. Yeah, correct. So here, this is the main part of this. If we have common element, then we are not shifting into the final list. We are skipping that. Okay. So based on that, I think you can conclude the option. So L3 contain all value that occurs in either A or B, but not in both. Okay. So last option is
correct.
Okay. So next, this is related to the selection sort. Selection sort is given fine. Which of the following statement are correct regard to the selection sort? Okay, selection sort is stable sort or not?
No, it is not a stable sort.
Selection sort is
not
not
a stable sort.
Yes. So first option is not correct. We are looking for the correct option. So first.
Sir, I forget this stable thing. Can you remind me?
So this seat is given in the, I think, week 3.
Stable means mutating or immutable?
No. This is not related to this. So stable means if your list have similar elements. Okay, like 2, 3, 1, 2, 4. So this input is given here. You have two similar elements, this 2 and 2. Okay, when you are sorting this list, the order of the similar elements should not be changed. Then algorithm is stable. If order of the similar elements is changed, then your algorithm is not stable. Okay, this is the definition of stable. So
yes, I remind.
Yeah, selection sort is not stable, and it is sort in place. Correct. Okay, so we are using the same list and we are performing the sorting in the same list without helping the other list. Okay, we are using the swapping operation. We are sorting. So that means option B is correct. First is not correct.
Can you please explain the stable definition of stable, please?
Stable definition. Okay.
Yeah.
So suppose when we are giving the input to the algorithm and your input contain the similar elements. Okay, similar element, that means the same value elements multiple times, and your algorithms will return the final sorted list. So like this 1, 2, 2, 3, 4. Okay, this is the sorted list output. So the order of this similar element should not be changed. Suppose if we give the naming for this is A and this
Sir,
is B.
you picked the wrong example. I think you should take example where 2 elements in each key. I mean pair of the element.
Yeah, tuple. You should take the tuples. That will be easy to explain.
Yes, list of a tuple.
Okay, that I'll explain. Yeah, so I'm just giving the example that we can explain with the other example also. So here, if suppose this 2 is, we are considering this is a and this is a B. So in the final sorted list, our first element should be this first one and this should be the second one. The order of the similar elements should not be changed. Okay. Now here you cannot identify by looking the only single value. Okay, if order is changed or not, but you can figure out these things by the algorithms. So just go through the algorithm concept and check if our algorithms can swap the elements or not. Similar element can our algorithm change the position or not. So
okay, thank you.
Okay, so I think some question can also be asked with the tuple of like this. We are giving like this 1A like this. Okay, and 2B, sorry, 2A. In this manner, some other value is also given with this. Okay, and we are sorting the list with the based on the first element. Then okay, let me just write the same example. So 2 comma A, this is the first tuple. Okay, and 3 comma A and 1 comma A and 2 comma B and 4 comma A, like this. Okay, suppose this is the list given to you in the input, and your task is to sort this list based on the first index value in the tuple. Okay, without helping the second index. So what your algorithm is actually returning. So suppose if your algorithm is returning like this, so 1 comma A and 2 comma A and 2 comma B and 3 comma A and 4 comma A. Okay, now you can see we are getting the same order of the so this 2A, this A is coming first and this B is coming after this. Same we are getting here. Okay, 2 is coming, this A is coming first and this B is coming after. So if our your algorithm is always return the same behavior, then your algorithm is stable. Otherwise, if your algorithm may return the answer like this, so 2 comma B and 2 comma A, like this, that algorithm is not a stable algorithm. Okay, so selection sort is not stable and sort in place. In selection sort, after m passes, okay, through the list, the first m elements in the list are in sorted order. Yeah, okay, so yeah, correct. So same what we are doing in the selection sort, we are just picking one position, we are finding out the minimum element and we are swapping this. Okay, so in one iteration, our one element is coming at the correct position, that is smallest element. Okay, and after second iteration, our two elements will come at the correct position. First two element, first sorted, first minimum and second minimum. So after m passes, our m elements will come in the correct or sorted order. First m elements. So this is also correct. In selection sort, after m passes through the list, the first m element in the list are the m smallest element of the list. Yeah, this is also correct, because all these first m elements are the first m smallest element. In selection sort, after m passes through the list, the last m element. So this is not correct. Okay, so last m element we cannot conclude according to this algorithm.
So could you please once more repeat what is the criteria for not stable?
If our order of the similar elements become change. So in the second example, suppose if our order is coming like this, so 1A, 2B, 2A, and 3A and 4A.
That would
So
only come if the initial list has the reverse order. Right?
so this is we are considering as a input list 2A. Okay, so this is first, this A is coming first, and this B is coming after that. Okay, so here similar elements are 2. Okay, first element we are considering as a and second element we are considering B. But in output sorted list, we are getting like this order. So 1A, 2B, 2A, 3A, 4A. So here you can see order of the similar elements are changed.
Yes, sir.
Okay, then algorithm is not stable.
Okay, sir. Okay.
Okay. Yeah, so these B, C, D are the correct answer for this. Okay, yeah, this is topological order based question. Yeah, so here in this question, so this is a little bit tricky if you have not enough practice. So we need to find out total number of ordering possible for this graph, and condition is also given here. So condition is that if 2 appears before 3 in any topological order, so then 8 must also be appear before 9. Okay, so what order are possible? If in any order, if 2 appears before 3, then we will also satisfy this condition in that order. It must be appear before 9. So by satisfying this condition, how many orders are possible for this graph? So let me take the screenshot for this. Okay, so we will start from the 1. Okay, how many such orderings are there? So we can write like this. We can also create the tree type of things for this. Okay, so like 1 is the first traversing order. So you know that in the topological ordering, we remove the elements and we check what are the other elements remaining with the in degree 0. We can select any one of them. So same things when we are so we will always start 1 because we have only one node available with the degree 0 in the initial. And but when we remove this one, we have two options. Okay, we have two options. So that means we can either move to this side 2, and we can either move to this side 3.
But in this question, it is not given how in which element should we start. I
But-
mean, there is no
so-
starting element.
Okay, so then which element you can start from this?
Let's say
If
start
we are
from
not
6.
starting from 1, then how you can start the other element?
Okay.
The in
Of
degree
course.
has to be 0, right?
Yes, in degree has to be.
Okay, and this is DAG actually. So you can start only with the in degree 0 node. Okay, so now then 2 you can select or 3 you can select. Okay, suppose if you select 2, this one, then that the new edge will remove to 6, but you have only one option to select 3. Correct? If you are selecting 2 after 1, so if you are selecting 1 then 2, then only you can one option is remaining with in degree 0 is 3, because this edge will also removed, but still 6 have in degree 1 from the 5 side. Okay.
Oh yes.
So in this manner you can move to 3, and then when you are moving to 3, then you have to only one option to move 4. Then if you are removing 4, you can only move to 5, and if you are removing 5, then you have to only select 6.
No, sir. If I go to select 3, then I can after that I can also select 2 also.
No, we have in this path we have already select 2 now, so we are looking for only this path.
No, this path is okay. Okay, for the
Okay,
second path.
we are looking
Correct.
only the one possibility. Okay, then we will check the another. Okay, so we have reached to 6 here. Okay, now we have 6. Now you have 2. When you remove this 6, so now that means you have available option for 7 and 9 both. That means 2 paths are available from this side. Okay, suppose if you select 7, okay, then you can also select 9, 8 and 9. Once again you have 2, 8 and 9. Correct? Both are available. If you select 8, then you have only option to select 9.
Yeah.
Okay, if you select 8, then you have only option 9, and after that 10. So this one path is completed in one. Suppose after 7, now we will move to the another possible path from the previous side. Okay, so after 7, when we are selecting 7, we have two options, 8 and 9, and we are selecting 9 this time. Okay, and after selecting 9, we have only one option, 8. Okay, suppose after 7 we are selecting 9, so after selecting this will be removed, so we are selecting 9, then we cannot select 10 because it's 10 have in degree 1 from 8, so we have to select 8 then 10. So this is another path possible. Okay,
Sir, but it says that if 2 has come before 3,
that path we will
8 has to come before 9.
that we will remove. Okay, that we will remove after that. First we are looking the all possible path. Okay, now this is the two possibility from the 7, and now we will move back from the 6. When we select the 7, then we have completed all the possibility. Now if we are selecting from 6 to 9, okay, we can select 9 here also. If we are selecting 9, then we have to go through from 7. Okay, then 7, then 8, then 10. We have only one path from this. Okay, now this is completed. Total,
Yes.
how many unique paths we have? 3 till now.
And what about this 3?
Yeah, we are
1,
solving
2.
this now. Okay, now we will check for this another path. If we are selecting 1, we have two options, 2 and 3. Suppose if we are selecting 3, okay, if we are selecting 3, now once again we have 2 and 4, because 2 still is not visited and 4 is also option we have. Okay, if you are selecting same things. Now after 3, if you are selecting 2, so you will get the same like this, 2, 2, and then you have option only 4, then 5, and the same things from the 6 you have the same option. You can no need to check again, because from 6 you have the same. 7, 9 you can write in the same manner. 8, 9, 10, and 9, 8, 10, and here 9, 7, 8, 10. Okay, so this is the another possibility with 2, because after 6 we are following the same approach which we have already done in the previous example. So if you are selecting to this path, now you get all 3 another. So but now we'll check the another possibility. So 1, 3, so 1, 3, and if you are selecting 4 first, okay, so then after 4 you have once again option 2 and 5.
Yeah.
Okay, and when you are selecting 2, then you will move to 5, and then 6, then again you have 3 options, same. Okay, in the similar manner.
So 2 options, right?
No, from 6 you have 3 na total, 3 separate, 7, 8, 9, 10,
Yeah.
and
Yeah.
yes, 7, 9, 8, 10, and sorry, this is not.
Yeah.
And 9. Okay, so okay, sorry, this is 7. 9, 7, 8, 10. Okay, yeah, this is done. Now we will check for the 5. So when we are now we have this option 5 and 2. Okay, if we are selecting 5, so we have to move to 2. We have no choice because we cannot select 6. And if we are selecting 2, then we have to select 6, and then we have 3 total. 7, the same, 8, 9, 10, and 9, 8, 10, and here from 6, this is 9, 7, 8.
I've got a question here, sir. After 2, shouldn't it be 6? Why are we coming to 3, 4, 5?
After 3, where?
After 2, it should be after 1. 1 is starting. After 1, it should be either 2 or 3, 4, 5. Correct?
Yes.
Okay. So so after 2, why are after 3 we should be 4, then 5, and then only it will come back to 2, right?
No, if you are selecting like 1, then 2. Okay.
No. So let's say I select 1 first, then I go to 3. Okay. After I go to 3, I cannot come back to 2, right? Or
so this order is also there now. So 1, 3, 2. This path you can see. Okay, this is also there. All possible path is there here now. So we have total 12 path. Okay, now check this condition. If 2 appears before 3, so where the 2 appears before 3?
Only the upper one, the first one.
So this one. Okay, so in this path you have to take this also. So 8 must appear before 9. So you can see 8 must appear before 9. So this is the only valid path.
Yeah.
Okay, now we have to remove this 2 path because this is not satisfying condition. So this 2 will be removed. So when you remove this 2, you will get total 10 unique distinct path.
So we have 10 paths to fulfill this condition.
Yes.
Because of this 10, if there would be an end, then we have only one path.
If this condition is not given, we have total possible 12 path.
And not full
No,
condition.
how it is 12?
I
Can you
want to
please
emphasize
explain?
the word then. 3 appears before 3, then 8 must be before 5.
Yeah. How 10 is coming? 2 must be 2 appears before 3 is only one case, right?
Yeah. So
it's
no,
only one case will come out of
no.
12.
No. The condition is if 2 appears before 3, then 8 must appear 9. So this is the condition. If this condition held, then this should also held. If this is first condition is not happening, then we will take that. That is else part is not given, na? So we will take all the possibility.
It is
Okay, so
implied condition, not end condition.
okay, so this one path we are getting from this side, and total 9 paths we are getting from this side.
So there is no other way to there's no
No,
shortcut.
can we
right?
can we read the question?
Huh. One second.
If we read the question, it does not say like that, right? Or I'm not too sure.
So we are interested in topological ordering of the following DAG, which satisfy the constraint that if 2 appears before 3, then 8 must appear before 9. How many such
Yeah,
ordering?
so that is the only case there we are interested in, right?
No, it does not say that what does happen when 3 comes before 2.
Yeah, it does not. I'm not too sure. This English is I'm not too sure how to take this. How
No,
we go
it is
on
saying that
thinking.
if this condition is satisfied, then this should be set done in the order. Okay.
But
if this is not satisfying, then we no need to check anything in the order.
No, we are interested in a topological ordering of the following DAG,
but if condition is
which
given,
satisfies this constraint.
Yeah.
No, we are
interested in only those which is satisfying the constraint, right?
No. If is there. If this happens, then this should also happen.
Yeah.
Yeah, but otherwise we are not. If this is not happening, then
no, that case is not mentioned. Okay, anyways, if it is you have to
it is
do it
only
like this,
limited that if 2 appears before 3. There can be cases where it doesn't appear, then we will simply take it as it is. We don't have
because
to remove it.
in the case 132, it does not violate the clause, right? Because 132, so we don't care if it is 8 is coming before 9 or not.
In this question, sir, the second condition becomes operative only when the first condition is fulfilled. Till the time the first condition is not there, there is no need to check the second constant.
Yes.
So 1 plus 9. But this question is more of equally an English question.
Yeah, exactly.
Yeah, this one we can interpret based on
It's a
people's
threadbare
It's not
English
a very
reading.
clear, straightforward question.
Okay, I think this is first term question, so we are also maintaining one proper clarity in the questions, and we are also trying to remove all the ambiguity in the questions. So maybe because this is the first term question, so maybe there's chance.
Sir,
But,
I tried these things, but there I found that there is another pattern that makes this question solution easy. Okay, but I am not sure that it is a generic or not.
Because of that, I have not tried any shortcut here, because this question is totally based on the graph connections.
No. See, 12 is clear. Only thing is, out of 12, what we are interested in? We are interested in.
I am not looking this. Someone is asking that any easy way to solve this question is or not.
Okay.
No, sir, so just a minute. If I am just trying to help, there is a two graph is there. Okay, one is up to 6, another is 6 to 10. Now, if you take the left section of the graph, that is 1, 2, 3, 4, 5, 6. Okay. Now, first eliminate. I try with the couple of the graph, then I don't have time, so I not go to the depth. So first take the path that is an unique path. So unique path is there is only one unique path. 1, 2, 3, 4, 5, 6.
So that means we are doing the same now. So we are writing all these 3 steps every time. So there's no need to calculate after.
Yes, sir.
So this is 3.
Yeah. So
we
now
can
in the
ignore this.
yes. So now in the second one, okay, you can write 1 dash. In a list, you can write 2, 3, 4, 5, and then you come to the 6. Now the path will be the permutation of 2, 3, 4, 5 with the only one constraint. Constraint is that 4 comes before 5. Okay. So if I go with this kind of concept,
this conceptual you are applying for this graph, because this graph you are finding that this is divided into 2 parts, but the graph may be any different
yeah, I agree.
okay?
I do agree, but I think there is some patterns are there, sir. I mean, I don't think.
No, this is the only way. This is the best way, so that people cannot make mistake.
Yeah,
This
because
is
of that
the
I mentioned this overall tree
no,
structure.
this is how I have resolved. But only my problem was this question. I did not find an
Yeah,
answer
this
because
may
for
be.
me the answer is one based on the question. For me, it's the only one option is there out of 12.
Yeah,
Option was not
exactly.
there, so I did not mark.
Actually, this is logical problem. In logic,
This
we
is
call
maybe
this
some
implied.
ambiguity in the statements. So yeah, you
Yes,
can
sir, it
consider it.
can be interpreted in both ways, with and without the sheet.
Yeah, because of that I said that in every terms now we are trying to remove all the ambiguity and we are trying to maintain the clarity in the statement. Okay, so you will not get this type of things. So in some way, if we get this type of ambiguity things in the final exam, so we generally reevaluate. Okay, so don't worry about this. So yeah, so this is the way you can apply for, and generally we not give too lengthy graph for this type of question. So maybe you will find maximum 10 or 5 or 4 topological order only. Okay, very small graph will be given to you, and then you can simply apply this tree logic to figure out all the paths.
But sir, my question is that why you are not going and find it is the permutation? Because there is only two patterns is possible in permutation.
But you are applying this logic into, yeah, you can apply. So I'm not stopping
No,
you.
so since I am a math guy, so I am not able to find
Yeah.
ultimate
If you are
solution.
finding that part, that PCG, so you can do this. But I am just explaining in the same graph behavior.
Yeah,
So I think you can
yeah.
understand. So, okay, but I think suppose sometimes if graph is not like this, if it is any other graph is there, no graph is there. Suppose these two connections are also added, so this 2 and 7 is connected and 5 and 9 is also connected, then you cannot figure out which part you have to break like this.
But also it will not be solvable by graph also. It will be too complicated
Then
graphic
it
graph.
will become too complicated. So because of that, we generally ask very small graph questions. So where you will only find out to maybe 6, 5 different topological order.
Okay.
Okay. So small graph we will give generally. So next, so this is okay. So this is simply properties based question. So algorithms are given and complexities are given. So just remember these basic properties of the each sorting algorithms. Okay. So I think you can figure out this best case, worst case, average case for insertion sort. So you know that insertion sort best case is order of n when the list is sorted or identical elements. So that is order of n. Otherwise, the worst or average case will remain order of n square. Selection sort behavior is same in the each case, each type of input, order of n square. Quick sort behavior is different for the if list is if your pivot elements comes in the one corner in the each partition process, so it become a worst case behavior for the quick sort. So in that case, your quick sort will take order of n square time. Okay. In the remaining case, it will take n log n time. But merge sort behavior will remain same for the each type of input. Okay, n log n time. So you can remember this property. So basic property about the complexity of the selection sort.
Any formulas will be given as an
formulas means
formulas for PDSA. There will be a section separately given,
like cheat sheet.
Yeah, something like that.
And no.
Oh, you mean to say like stats too? No, I don't think so.
No.
Okay.
So on this question, on top of this, can you tell us like that in place sorting, which all algorithm is having in place
So
sort?
in place actually selection sort, if you see the implementation of selection sort, insertion sort, we are using the same list and we are performing the sorting by the swapping the elements. Okay, and we are not using any additional list. So that is called as a in place sort. And the same for the quick sort also. Quick sort we are also performing the in place sort because we are performing the partition and same all the things are on the same input list without using any additional list. But in merge sort actually we are passing separate list, new list into our recursive functions. Okay, in that case, new list is actually created, and that merging is happening on the new list, and separate space we are taking for the sorting. So merge sort is actually not in place sort.
Correct. And on top of it, I think merge sort takes more memory, right? Since it's
Yes, more
creating one
memory, space memory. Yeah, correct.
So, sir,
and less. Yeah, just a second. Um, so merge sort and the other three sorts takes less memory in that case, correct?
In place, yeah. Correct.
so sir, the merge sort will be the only stable sort out of this four.
No. Quick sort. Check. Selection sort is not stable, but insertion sort is also stable. Let me open the summary. Week 3. Insertion sort is also stable. Selection sort and quick sort is not stable. Okay, you can see this table. So selection sort is not stable, insertion sort is stable, merge sort is stable, but quick sort is not stable. So merge sort also we are not changing the sequence if we have the similar element.
In quick sort.
Hmm.
Okay, so got it. No, nothing.
Okay. Yeah, insertion sort also we are not changing the position if we have similar elements.
Stable means that the position of the elements remain the same, right?
Similar elements.
Similar.
Okay. So the things. Yeah. So this question, last question. Yeah, 15. So the 15 is actually related to the you have two-dimensional matrix, and you are sorting the elements. Okay, sorted in increasing order, left to right, then next row left from top to bottom. Okay, so your list is matrix is given in the sorted order, so left to right, then next row is left to right in this manner. Okay, and what will be the efficient algorithm for the binary search? If you want to apply the binary search on this type of list, if x is present or not, then what would be the complexity? So first thing, you can figure out the range which actually rows should you should check. Okay, because each matrix, each row, you have some starting element and last element position. You can let me just, okay, like your elements are arranged in this manner: 1 2 3 4 5 6 7 8 9 10 11 12, like this. So what you can do first, you can figure out the number of rows in log n time. Okay, so number of rows are suppose n, so you can apply the log n steps to find out the number of rows.
Yeah.
Okay, so you can simply compare the elements first and last. If you're searching like 9 elements, check this 9 is coming in between 1 and 5 or not, and then you can move. So first select the mid rows, okay, and check.
Yeah.
And you can apply the binary search on the rows and find out which rows actually contain the element. After that, apply the binary search on the columns for particular row. That will take log. So if number of rows are m and number of columns are n, the total will be log m plus log n.
Oh, why not times?
What?
Why not option B, like log m times log n?
Both are correct, no? In this question, I think both are correct.
No, sir.
No, sir.
No.
Why both are correct?
Log m
Because
into
we are
Option A is correct, then option C should be correct.
no,
Because
only
according
one
to maths,
options.
yeah, option A and C should be correct if both are
Why?
correct. Because that's the property, no? Log m.
Oh, okay.
Yeah, this is the property log. You can also write in this manner.
Yes.
Sir, or B will be correct, sir.
No, B will not be correct. Here we are not multiplying this. Log m into log n is how this is happening.
Sir, we will either search column or search row, apply binary search on each.
So
each will
first,
take log m and log m and log n. So
no, first you have to figure out the which rows actually contain our x element. Okay, so that will take log m time. So this part is now completed. Then you will start the column comparison by the binary search. So that means one part is now completed, then you are starting the second part, and the first part is taking log m time, then second part is taking log n time. So this will be add, not multiply.
Yes.
Okay. And this is stack based question. So this type of question, simply you can take one stack and you can apply the all operations sequentially. So initially, suppose you have this push 10 means you will insert 10, then 20 will come on the top of this pop. Okay, so this 20 will remove first, so this will be removed. Now once again 10, okay, and push 20, 20 will come at the top, then pop three times, so 20 will remove first, then 10 will remove, then 10 will remove. Okay, so your stack will become empty. Then push 20 and pop, so 20 will remove. So what is asking this? Okay, pop sequence, so 20, then 20, 10, 10, then 20, this like. Okay?
Option B.
Option B.
I hope this question comes.
This type of question will come, yeah. Similar type of, and the mock level is actually very high compared to the actual paper. So
okay,
don't relate the comparison because you have enough time to practice for this. Okay, but in exam you have only 45 or 1 hour.
Yeah.
So
I
okay, so
have some PYQ questions I have.
so now you can share your doubt.
Now, one question I have here: the PYQs, whatever are there, are they similar to this particular mock that you sent?
No, actually, these mock questions we have taken from the different previous year questions. Okay, and this is mostly from the first term or second terms. At that time, the level was high compared to the current terms.
Oh, okay.
So, but overall paper will be, maybe you will get some easy questions, some moderate questions, some maybe 2-3 questions are challenge like.
Okay. All right. Thank you.
Sir, where can we find the recording of today's session? Because I joined a little late when we were discussing question number 8. Is there a recording available somewhere?
Yes, it will be available in the calendar and on the YouTube also. Okay, YouTube. Okay, I'll copy this in the event.
Sir, also, sir, I have one question on the previous year question. It has posted in the disclosure, but somebody give very good answer. Still, I don't understand, so I don't drag it.
One second. Let me just. Okay, so link I have pasted in the calendar event. You can see. Yeah, what is this question? Okay, just.
Actually, this how to proceed with this? Which of the following cannot be? This is already we know we've given the
So
list
in this
of
question,
keys.
actually, in this question, the output is given. Input sequence, insertion sequence is asking. Okay, so this question will be solved by the option.
Okay, this one is the input, and then this is the output. So we
So
have
that
to
table is
apply
actually,
each and everything, and then see whether this is coming.
So 1 second, give me a. I'm taking the snapshot for this, and I'll explain.
Because 2-3 questions have come in this type.
So one hashing question you can expect in the quiz. Okay. So let me share my screen.
Yeah, I'll remove.
Oh, my screen is already visible now. Okay.
No, sir. You
No, sir. Your screen is invisible.
My screen is not visible.
No.
No, sir.
No, sir.
Stop screen. 1 second.
Yes, it is visible.
So yeah, this question. So what happening here? Table is given. Okay. So and elements are also given with the corresponding table. So let me just write this. So 0. And elements are also given, so that this is the output. Actually 72 is stored here, and 23, 12, 54, 36, and 83. So this order is given. So this is the output hash table. Now some sequence of input is given. So for which input actually, so what is asking, which of the following option cannot be possible order in which the key could have been inserted in the hash table. Okay, so that means what order is incorrect here, so you will not get the given output by the, if you insert the element in the given order. So we will check option wise. Okay, so this question you have to solve from the option. So suppose now I am making, suppose this is the part where I'll just store the data. So this is empty now initially. Okay, for the first option. So you have order given 23, 36, 72, 12, 54, and 83. So this is the inserted order. So first you have empty hash table, and now 23 the first input data, and the mod function is k mod 10. Okay, so 23 mod 10, what you will get 3, correct? So that means if you insert this element into the hash table, you will apply 23 mod 10. So 3 remainder will come, and that means at 3 index you have to store this data 23, correct? Now second element 36. 36 mod 10, you will get 6. So that means 6 is empty. So 36 will be inserted at here. 72 mod 10, you will get 2. 2 is free. So 72 will be inserted here. And then 12. 12, again you are getting 2. Okay. Now collision is happening. 2 is already occupied by 72. In this case, according to the linear probing, okay, so linear. Okay. Linear probing, yeah. According to the linear probing, is the that index is not available, then we check the next index after this. Okay, so that is available or not. So we will repeat this process until we will not get the empty space. So that 2 index is not available for this 12, then we will check the 3. 3 is also not available, then we will check the 4. Yeah, 4 is available, so this 12 will store at this place. Okay. Now 54, we are getting 54 mod 10, 4. So 4 is still now occupied by 12. Then we will check the next index of this. So 5. So 54 will come here. Now 83 will return 3. So 3 is already occupied, 4 is already occupied, 5 is already occupied, 6 is also there, and 7. So 7 is empty. So this 83 will come here. So you can see when we are following the first option, we are getting the same similar positions for each element as the given input table. Okay, so that means this is the correct one. But if you're looking for the option 3, so order 36, 23, 72, 12, 83, 54. Okay, now I'll fill here in this side. So 36, 6. Okay, so 36 will put here because initially all are empty. 23 will return 3. So 3 it will come here. 72 will return 2. So at this time this is also available. So 72 will insert here. Now 12. Now 2 is already occupied. 3 is all occupied. Now 4. 12 will come here. Correct. 8. No, 83. Okay, 83. 3. But 3 is already occupied. 4 is already occupied. Now 5 is available. So you can see 83 should come here. Now 54. So 4 is already occupied. 5 is also there. 6 is also there. Then 7. So this 54 should come according to here. Now you can see for option 3, you are getting this positions for the element. Now this is not matched with the input table. 72, 23, 12 are matched, but you can see then 83. But output is coming 54 at this place, index 5. Okay, so for which input actually you are not getting the similar output hash table which is given in the question. So that option is the correct option according to the question. Okay, so just follow the same process of the insertion in the empty hash table and check you are getting the same positions as per given input table or not. Is it okay?
I can share the next question.
Yes, yeah.
Sir, in the same question, sir, how actually we derive the hash function?
Hash function is given. Hash function is given in the problem statement.
Yeah, not the exam point of view, the actual when we have some data, what is the basis of finding a hash function?
So this is just this hash function we are taking for just explaining the top concept of hashing. Okay, otherwise in the normals dictionary which we are using in the Python, actually we takes the complex hash function where our hash function will return a minimum number of collisions. So actually collisions are the main criteria for the hashing deciding the hashing function. Okay,
Okay, this
so
SHA
sorry, yes, SHA
256 or something.
yes.
What exactly that is? Is that just a function?
That is also a hashing function or hashing formula. You can say that based on the input, some formula we are applying for that input, and that is returning some output index or place or output address. But that address should always be written as a unique address. That should not return as a collision like this. Okay, and the same actually hashing or this encryption things also we used in the networking or this type of thing. So we use this encryption techniques and we convert the main text data into the cipher text that in the different forms by some formulas or some like conversions. Okay, but that conversions should be happen in the complex way so anyone cannot hack. So that is regarding to the encryption, but hashing is also similar to these things. We are now figuring out the index or address.
Yeah, one more thing, sir. This is that stored as
Sorry?
a linked list?
No,
Sir,
can you repeat? Your voice is break in between.
sorry. How actually the data is stored? It's stored as a linked list.
No, it is based on the memory structure. How we are actually how our language is managing the memory. So that it depends on the memory management. So what data structure they are maintaining, how they are what mapping they are using direct that mapping addressing this.
Because if you are not using linear or
Actually, we are maintaining
quadratic
one.
or
We
some
are
other situation,
maintaining one.
so we might be pointing to a bigger index.
We are actually maintaining one hash table. So using that hash table, we are figuring out that where our data is actually stored. Okay. So yeah, chaining is also there in hashing. There is one technique we generally use the chaining that contains the data in the linked list manner. So that techniques is defined by the that manufacturer or that algorithm, those who are designing the systems, how they are managing the memory.
Yeah, okay, thanks, sir.
This question, this I'm not able to understand
recursive structure.
Because the fun queue is coming recursively based on this. Then how it is reversing this list?
Okay. Okay. So my screen is visible now. Can you see? My screen is visible?
Yes, sir.
Okay, so for recursive structure, you have to imagination a little bit. Okay, so how actually this recursive happens. So this is the main function we have, this function part. Okay, initially what element we have in the queue? 5, 5 and 3, 7, 2, 8, 1 and 4. Okay, this is the queue. So queue means
Excuse your screen not.
Hello, my screen is not visible.
No, sir.
Visible.
Okay, you have to just okay, pin the 1 second. Okay, so this is the queue which is given, and how our queue operation is performing. So which where we are adding and where from we are removing. Okay, so just note down this thing. So our queue in queue process, in queue means inserting the new element. So that means we are adding the element from the end of the list, and we are removing the element from the first position. So dq is actually just a pop 0. Okay, so we will remove the element from this side. Okay, so just remember these things. We are performing queue in this manner. Now this is the recursive function, and in recursive function we are starting from if queue is not empty. Okay, then we are performing this operation. So first call, I am writing the first call fun queue, and we have condition if queue is not empty. Okay, so initially queue is not empty. Now we are performing this first we are performing dq operation, and we are meant storing the data in I. So that means dq, okay, q dot dq. So one element will be removed from this at this time. Okay, so that I will become 5 here. Now we are passing this, we are calling the recursive function here. Okay, now at this time we are calling the function, and now this time our queue contains this list 3 7 2 8 1 and 4. Correct, because we have removed one element at this position, that our I become 5 by the first element. Now this is the next call, next recursive call, and we are not performing the last operation because we have the call, and we are moving the say from this call. Now this is the new function. So function, and this is the new queue list. So okay, I'll write queue in the top. So this is 3 7 2 8 1 4. Okay, inside this function still this is not empty. Then our new I element will remove the one element from the first position. So this will become 3. Okay, and we will pass fun q. Now our q, this is the next call. Okay, so function, we are passing the list with 7 2 8 1 4. So I am just following the flow of execution by this structure. Okay, so once again, now this is the new function we are passing, and this is still not empty. So I will become dq. So dq, again remove the one element 7, and next call fun. Okay, so this is next call. That means fun 2 8 1 4. Okay, again this is not empty, so I will become one dq option. So this 2 will come, and fun q. Okay, updated q will pass. Next fun, and list is now 8 1 and 4. Okay, and again the same code will start. So I will become 8 this time, and once next call. So this is next recursive call. So fun 1 and 4. Okay, and here I equal to 1 and fun q, and next call fun, this is 4. Okay, and I become 4. Now you can see we are passing fun q, but now this q will become empty after performing this one dq operation before this. So in this next iteration, this fun uh, q. Okay, so yeah, this is empty q. Okay, in this case the if condition is not satisfied because our queue is not empty now, so no operation will perform here. So this means this is the empty part. Now here our this recursive call is complete. So this is the base case actually of this recursive call. So this part is now completed, no recursive call after that. So we will move back and we will perform the next operation, which is performing at the last as a third operation in our main function. So third operation is here is q dot inqi. Okay, q dot inqi. So q is at this place, q is now empty. Okay, and we are performing inq operation with q. Okay, so that means I, what is the current value of I is now 4. That means we are in q 4 into the q, so our q will become 4. Okay, we will always add from the end. Okay, so at this place, now this function is completed, we will move back to the previous. So at this place, in the previous position, at this previous position, now I is 1. Okay, and we are performing q dot in q. Okay, in q 1. So that means we are in q 1 element into the q. So the element we have q in the 4, and we will insert 1 into this. Okay, so our q will update it like this. So 4 comma 1 from this. Okay, so 1 will be adding from the end. Now this part is, this function is completed. Now we will move back, and here operation is q dot in q 8. Okay, so I is equal to 8 here. Now our q will update like this. So 4 comma 1 comma 8. Okay, and here q dot in q 2. So our q will become 4 comma 1 comma 8 comma 2. Okay, now this is completed. Reverse back. So q dot in q 7. So our q will be updated like this. So 4 1 8 2 7. Okay, now this is completed. We will reverse back to the previous. So here q dot in q 3. So our q will update it like this. So 4 1 8 2 7 comma 3. Okay, and the last operation. So move back here. So q dot in q 5. Okay, and this is the 4 1 8 2 7 3 5. Okay, and now this is the updated one. So in this manner, our flow execution is happening in the recursive call. So our output, so what will be the state of the queue after the execution of function queue? So this should be the state of the queue: 4 1 8 2 7 3 5, like this. Okay,
Thank you. Last one, last question.
Yes, here please.
This is also same kind of a fun function only, but it is a bit different fun function. It's with linked list.
Okay, so what you're saying, this is linked with the linked list, you're saying? Okay.
It's the same fun, same. It also reverses, but I'm not able to figure out this.
Okay. Okay, so you can stop sharing. Okay, so yeah, this is the code. So assume we have a class linked list with head refers to the first node of the linked list. Method fun is given. So self current node previous node is defined as a linked list class. Okay, and then value fine. So yeah, this function is given. So initially current node or previous node. Current node next. Okay. So initial state of the linked list is given. So like this is head, and head contain the first node that contain 34. Okay, and next node contain 12. Next node contain 67. Next is 9. Next is 12. And next is 4. 4. Okay. So this is our input linked list. Okay. So now the code is, one second.
Hello.
Yeah, sorry for. Okay. Yeah, my screen is visible. Okay. So we will just look the code and we will apply the dry run on this. So we have the linked list structure now. So current node. Okay. So this.
I have a request. Can you zoom in a little, please? I'm barely able to see it.
Okay. So this is actually a blur image little bit.
Okay, that's better. Thank you.
So what we are passing in this, we are passing head, okay, and none. Okay, so that means current node contain that current node pointer contain the uh, head.
What is this first parameter, sir? One or what
No,
is this?
L dot head. So L is the list.
Okay, okay. I
Okay, and
cannot
dot
see.
head. Head is the first element. So that is this is pointing to the this first node, and that none we are passing to the prev node. So prev is node actually contain the none initially. So this is the function we are passing. Now we are checking if current node dot next is none. Okay, so if this condition is true, then what we will do, we will shift our self dot head equal to current node. What we are doing. Self function. This is self dot function type.
No, in the first step, it will not be none, right? Because current node is ahead, which will be pointing to
Okay,
another
okay, yeah, fine, yes,
node
correct.
12.
Yeah,
So
so
it
first
will not go
condition
to
is yeah in
it
yeah
will go
in
to the temp
huh.
for all the. I'm not able to.
Okay, okay,
How
fine.
it goes, and I'm not able to. I
So
tried. I'm not able to do.
in first condition, this first is not satisfied because current node is pointing to the head, not none.
Yes.
Okay. Now
Yes.
we will set our temp equal to current node dot next. So current
Yes.
node is 34, and next will point our this second node. Okay.
Yes.
Next will move to this. Now current node dot next equal to
No, current node dot
temp.
next
This
will be none, right? Because previous node we passed none currently. Temp will be having 12.
One second.
Current node.
No, current node contain the head, na? So head means the first node. Okay,
No.
if we so current node dot next, so current node next is this address. So this address is for 12.
Yes.
Okay, so our temp will contain the address of the second element. Okay,
Okay.
now we are shifting our current node dot next equal to previous node. So previous node is now okay. So this is the new current
Yes.
node next equal to the
Previous node is
previous node.
having none.
Okay, okay. I think then we are got the we
You
are
are
trying
just
to
reversing the direction of these arrows.
actually we are just changing the we are reversing the address. So what we are doing,
Yeah.
we are setting current dot next. So this place we are setting previous node. So what is the value of previous node? None. Okay. So that means our link is removed. Okay. So this link is removed because we have set this none here.
Yes.
Okay. And now the we are passing the recursive call self dot fun equal to temp and current node. Then that means that now this current node become temp. Okay, in the next call. Okay,
Yes.
current node cn.
So
I'm writing
we
cn.
passing 12
And this current node will become the previous node. Okay, so that means this previous node is this. This will become a CUR current node. Okay, the previous node. Okay, previous node. And current node is pointing to this. Now in the same, we will repeat the same things. Now the first condition will be current node dot next is none. So still this is not true.
In the first iteration, it will be self dot fund will be having 12 comma. What will be the argument for current node?
No, this is not 12. Actually, this is address of the second node. So this will be the address of the second node, and this will
Address
pass
of the second node, and the current node will be holding what?
This previous element. No, current node was the previous element, the 34. So this will become previous node of this.
But we don't define that anywhere, right?
No, we have defined. No? So actually, we are passing current node. What was the current node in the previous call?
Okay, 34. Okay.
So now we are passing that value at the place of previous node.
Okay.
So this will become in the new call. It will become, so this is like a repetition call. So in the next call, fun, our current node will become 12 and previous node will become 34.
So just to clarify, in the first absolute first case, the current like the first if pattern runs, and for the next ones, the if block doesn't run, right?
You're talking about this part?
Yes, that runs only for the first time, right?
No. This will not run first time. This will run last time.
The last that will run, but I'm not able to understand how this is getting swapped.
Why? Like if the current node dot next, that is
no,
initially
actually
not defined, right?
this is called defined. We are passing this function. You can see in the call we are passing L dot head we are passing, and previous node we are passing none. So head is actually not none. Okay,
It is a reverse list, isn't it? It's not.
Yeah, we are reversing the list actually.
It's not a double-headed pointer. I mean, pointers back and forth, but it is in the opposite direction that you're keeping the pointers.
Actually, we are just we are reversing
the address. Yeah.
Okay, so let me just keep simple by the argument. Okay, so we are passing head, and head contain 34. Okay, so first call actually contain fun 34. Okay, and none. This is the first call, none. And when we are moving inside this, so what we are setting, we are so this first condition is not true. Current node dot next. So current node is 34. Okay, so this is Cn and this is previous node Pn. So current node dot next. So 34 next node is 12. This is not none. So that means first part is not true. So we will set our temp equal to current node dot next. Okay, so temp will become 12. Okay, and current dot next will become previous node. So that means we are changing this address in the list. Okay, so 30, this part will become none. Okay, in the first iteration. And in next call, what in the recursive call, what we are doing, we are passing fun and temp value. So what is the temp value is 12. Okay, and current value in the previous call was 34. Okay, so this will become 34. So this is now current node, and this is the previous node in the next call. Okay, same things. The current node dot next is not none. So first part will be ignored, and temp we will set to current node dot next. Okay, so 12 next node is 67. So 67, and current node dot next equal to previous node. So what was the previous node? 34. So we will set this pointer to the previous node. So this direction will become reverse. So that means 12 dot next will become previous of 34. So this link will become reverse here in the back side. Okay, now the next recursive call, we will pass function fun, and temp, what is the temp value? 67, and current node is now 12. Okay, same. So cn, this is current, this is previous node.
So every call we just reversing
the link
node and then point to the backward.
Yes.
And then we already made 34 next as none.
None, and we are setting this into here like this.
How we are going to move the head to the last.
So at that time, actually, when we will reach at the last point, no? So in the each call, we are shifting in this
manner. That is having none. Okay, so it will hit the first loop if not equal to none.
So when we are reaching at this position, so like at this position, this will become current. Okay, so fun 4. Okay, and previous node is 12. So when we will check this, what is the current node dot next equal to none? Yes.
It will be
Okay, at this,
none.
yes.
So what it will do that time?
So at the time, the first part will perform.
Yeah, first part will.
Self dot head will become current node. So our self dot head become that last node in this place. Okay.
Okay. So we move the head to this.
So head now will point to this. Okay, so our list will become reverse, and now when we will traverse this list, so we will get the reverse order of the element.
You are getting the head. Okay, that is why you are.
So 4, 12, 9, 16.
Thank you, sir. Thank you very much.
Okay, so this type of question, just take the input and just relate the code to the corresponding input. Okay, so how the working is happening.
Thank you.
Any other? Okay. Any other query in any question, previous time question?
Sir, one of us sent his query in this chat box. In Discord.
Let me discourse or chat?
Amitabh, in this chat. Amitabh Bhattacharya. Yes, this.
Okay, discourse query.
But he is no more in our call now.
So which query, actually here some explanation is also given. Okay, take a wow. This is great explanation.
But he couldn't understand this solution. That's what.
So this is regarding this question?
Yes.
Okay, let me explain. Okay, so what we are asking here is which of the following option correctly mention the return value total. So we are not asking the complexity for this code. Okay, so first thing we are asking the total value for the function. In terms of n, consider that input n equal to the power k, where k is a positive integer. Okay. And now what we are doing, so in the code, total equal to 0 initially, and we are running for I in range n by 2 to n. Okay, so n by 2 to n. Okay, then what is doing? So it will become 2 to the power k minus 1 if we are doing n by 2.
Yes. 2 to the power k minus 1 to 2 to the power k.
2 to the power k.
Why is it k minus 1?
We are dividing by 2 now.
Yeah, but
this is actually 2 to the power k.
Yeah, but dividing by 2 power k, but why k minus 1 is what I was trying to understand.
No, if we have 2 to the power like 4 and we are dividing by 2, so it will come 2 to the power 3.
Okay.
Yeah, because of that. So j equal to 2, now we are setting, and okay, for so while condition is given j is less than equal to n. J loop we are starting from 2 when the 2 is less than equal to 2 to the power k. Okay, and total we are adding every time inside this loop. So 0 equal to 0 plus n by 2. So 2 to the power k minus 1 we are adding. Okay, and j now we are incrementing by 2. J equal to 2. Every time we are just doubling the j value. Okay, so it will take and return total. So this you can see for each iteration of the I. So in the later part we are not depending on the I. Okay, so that means our loop will run overall total this 2 to the power k minus 1 to k times.
It's, I think, will run log n time because
Okay,
it's doubling
and the lower part will run. So this j value is actually doubling at every time. So we have n value is 2 to the power k. So what will be the log n steps first? So log n means log
it
2 to
will
the power
run
k.
k time.
Okay, so it will become k times. Okay, and we are adding. So this loop will run actually k times, and we are adding every time this 2k minus 1. Okay, so this is a little bit complex. Okay, total equal to total plus n by 2. So n by 2, n means is 2 to the power k by 2 into k times.
Yes.
Okay, so I think it become equal, no? So 2 to, oh no, k times. Okay, so this will become 2 to the power k minus 1 into k. Correct?
And it will run n by 2 times.
So this will run total of 2 to the power k minus 1
time.
1 times. So now we have 2 to the power k minus 1 and 2 to the power k minus 1 into k. So this is equivalent to 2 to the power k.
We unnecessarily convert this n term in k because answer is in n term.
So 2 into 2 to the power k minus 1. Actually, we are multiplying this. No, we cannot
So it
write
will
in
add
this way.
2k minus 2. 2 की power 2k minus 2.
No, if we are writing 2 to the power k minus 1 into 2 to the power k minus 1 into k. So this is the equation. Now we can...
We are adding n by 2, n log n times n by 2 we are adding. Because the loop run n log n times, right? And then every time it runs, we add n by 2. That's what we added to total. The total is getting added n by 2. The number of times we run the loop. Right.
Yep. The total, the loop runs n by 2 into log n times. So n by 2 log n, and we are adding n by 2 every time. So it is n by 2 into n by 2 log n. So n square log n by 4.
Okay, so you are calculating in the terms of
n.
Because it is
It is
addition
easy.
we are adding this many. How many times we are running the loop? We are adding n by 2. So,
n by 2.
It is
Okay.
n log n by 2 times n by 2.
Let's calculate in term of n from the beginning.
See,
okay, so if we will calculate that in the terms of n, then I think that will become easy, because we have converted into the terms of k. So you are correct. N by 2 we are adding, and this loop will run total number of log n times. Correct?
So it will be n by 2 into log n, the inner loop.
N by 2
the outer loop is,
log n.
So the outer loop is running n by 2 times, because it is
N by
fast
2.
n by 2 to n. So it is again running. So n by 2 into n by 2.
Yes. Yeah, correct.
Yes.
N by 2.
Yes.
It become easy, but I don't know why this n equal to the power k is given.
Yeah, that is given, sir, just to
Just to confuse us, and then
it can be proper log n, right? No, only if it is given, then we can know that, right? It's a proper log n.
This is also valid point.
One question: how did we come to log n if it is a total that we're actually computing here?
Actually, what we are starting j from 2, okay, and every time we are multiplying by 2 this j. That means j value will become doubled every times. Okay, so this 2, then 4, then 8, like this, in this manner. So we will reach to the n terms till log n steps. Okay. So how many steps are required? Suppose if you have 2 value and you want to reach at the 16, so 2, then 4, then 8, then 16. Okay, so log n steps 4 steps are required. So we can say that we will reach this 2 to n in log n steps. So this while loop will run actually log n times, and each time we will are adding n by 2 into the initial value. Okay, so total value will be n by 2 into log n, and the upper loop is running n by 2
times.
Okay,
N
so
by
that
2
n by
log
2.
n, and
yeah, so total become n square by log n by 4.
So basically, geometric rate is what I would actually call as logarithmic, is it? If the base is 2. Okay.
Yeah. I have confused with this 2k because the k is given, but we are just calculating them in terms of n, then we can directly use. Okay.
That's the normal way of question, right?
Mhm.
All these quizzes, they try to confuse.
No,
They
no,
don't
not
ask direct.
not that much. Okay.
Sir,
So
what is
this
the
is given.
complexity?
This is given because of you can conclude the complexity in the terms of log n actually because of that this value is given into the power of 2. Okay, so you can conclude that into a log n terms.
Sir, what is the complexity of only while loop?
N log n.
No, the
N
while
by
loop
2
is
log n.
No,
log n.
log n.
Log n.
If you're talking the complexity, then we can say that this lower part will take n log n.
No, it will take only log n times, not
Log
n
n.
log n times.
Oh, while no.
While is log n only, right?
Oh yeah, correct. Log n,
The
log
time
log. Yeah,
complexity
So we
complexity is
is
log
divide
n.
only. Yeah.
Yeah, complexity is log n, correct. Complexity of inner part is log n, and n by 2 steps are above, so overall will become n log n. But here we are asking the value of total, so that is actually different.
Sir,
Mhm.
the total value of while is only log n. Am I right?
No.
No. See, the while loop is running for log n times, and for log n times you are adding n by 2. So it is log n into n by 2.
Sir, maybe you explain the way you normally explain step by step. Maybe it will be easier.
Okay. So actually in this question, just do not conclude that we are asking the complexity. Here we are asking the total value. Okay, so here one variable we are using total, and what will be the value of total final when the this code will terminate. So in this case, so first loop, this loop is running. Okay, so I loop, and this loop is starting from n by 2 to n. So we can see that the total number of steps required for the I loop is n by 2 overall. Okay, and after that you can see the inner part is not depends on the n I value, so that means this will run separately inside the I loop, so we can find out the complexity of the lower part separately. Okay, so we are starting j equal to 2. Okay, and we will run this loop when j is less than equal to n. Okay, and every time we are adding total equal to total plus n by 2, so in each iteration we are adding this n by 2 value in the total, and our j value is incrementing uh, in the multiplication of 2. So okay, so initially j equal to 2, next step j will become 4, then will become 8, then 16. In this manner it will reach n. Okay, so these steps are actually how many steps we will reach till n, that is actually log n. Okay, so that means this while loop is running log n times, log n steps, and each steps we are adding n by 2 in the total. So total is starting from 0, and if you add n by 2 log n times, so it will become n by 2 log n. Okay, so this is the internal part, only one iteration we are talking about. In one iteration of the while, we will get the total value n by 2 into log n. This is clear?
Yes,
for
sir.
for one step we have n by 2. Okay, second step we have n by 2, third step we have n by 2. We have total log n steps, so total when you add all these steps, so you will get n by 2 log n. Okay, now this is the internal part. For one value of I, we are getting n by 2 log n value for the total, and we will repeat this process n by 2 times. Okay, so we will multiply n by 2 also in this. So in this manner you will get n square log n by 4. Okay,
Yes, sir.
so you will get the total value. But if we talk about the complexity of this code in the terms of n, then complexity will be different, because this while loop is only running because this is now become constant operation. Okay, this is constant operation, this is also a constant operation. So while loop will run log n time, and for each value of I we are running log n times, and we have total n by 2 steps, and for each step we are running log n times, so total steps will be n by 2 log n, and we can write this become n log n. Complexity will become n log n of this code.
Okay, sir, it's clear.
Okay. Okay, any other query? So this is discussed.
Sir, deadline of this white week 5 graded assignment has been increased, I think.
Not sure. Week
It's
5.
3 of March.
But I have seen week 5, week 6 having same deadline.
Same
Sir.
So actually week 5 is extended to the same week 6.
How it will be possible?
No, it
because of this exam.
no,
But,
actually
after the exam, how we can within 1 week, how we will be able to finish 2 assignments? Will not be having time to even watch the videos.
It's true.
okay, so one session, I think the content is not covered in the Wednesday session of week 5. So we will conduct one extra session to complete that part.
Or at
Honestly,
least
I'm
by
skipping all the
Wednesday or
sessions.
Yes,
Thursday following week would be better, sir, please.
So maybe Monday or Tuesday we will
Yeah,
try to.
Sunday will be very difficult. Maybe
Yeah.
Wednesday, Thursday at least.
So next Wednesday we will discuss week 6, but before Wednesday we will conduct for week 5.
yes, sir. Week 5 is very important. I couldn't understand.
Okay.
Okay. Thank you, sir.
Okay.
Thank you.
Okay. Thanks everyone.
Thank you.
Bye.
Thank you, sir.